What is good, everyone? Thank you very much for joining. Let's go ahead and get started here. Uh, Also, gonna go ahead and put on some background music here. Let's go ahead and put this on. There we go. Don't want to have it too loud here. Hello, everyone. Thank you so much for joining. Let's go ahead. Don't want to have it super loud. There we go. Okay. Hey, everyone. My name is Rad Nomad. As you can tell from the title of this stream, um, today I wanted to do something a little bit different. I wanted to kind of go over a subject that has a lot of meaning to me personally, which is math. So I think when I tell people that I'm like very into math and consider it like kind of a little bit of a passion of mine, I think some people are. It gives some people pause because I think a lot of people will look back on their own experiences with math and think, oh, that was something that was really difficult or something that they never understood. And I do sympathize with that a lot. There were definitely a lot of concepts that took me a while to kind of wrap my head around. I'd argue that I still don't have a great grasp around it. I don't know how well I'm going to be able to cover even what I'm talking about today. But I've also found that math, at least for me, has kind of been one of the more rewarding, I think, studies, at least in the time that I've been in school. Um, I feel like when I finally understand something related to math, it's almost a little bit like I don't know. I feel like I've unlocked like a piece of the universe or something. I think there's something very beautiful in how we as humans have kind of come up with different types of math and have I don't know, just our the way that our relationship with math has kind of grown over the years. Some of the very weird things we've identified in math. Um, and that's honestly kind of what draws my attention to math the most. Is just the really weird stuff, the stuff that doesn't make a ton of sense, at least on its surface. So this is one of those subjects that the first time I heard about it, I was like, "What the hell? Like, what does any of this even mean?" So yeah, I'd like to spend a little bit of time kind of digging into it. I am not going to claim to be any sort of math expert, you know. I'm not a mathematician by trade. I am more of an engineer. Most of the math in my job is fairly straightforward, mostly a lot of kind of statistics and like modeling and stuff like that. Um, but it's something that I like spending my spare time doing, you know, like looking into. I watch a lot of maths related videos on YouTube. Um, Mostly number file and three blue, one brown, excuse me. Um, so yeah, um, what I'm gonna kind of go over today is gonna be very basic, or at least kind of the most basic summary that I can give. That's probably a better way of phrasing it. None of this is basic math. Um, but yeah, I think we can go in and get started. Hello, Zaf. Thank you very much for joining. Need to take a shower? Yeah, go right ahead. Oh, I'll go ahead and also before you dive into the math lesson. Yeah, that's totally understandable. One thing I will advertise here, and I realize I probably should have included this on the stream description as well. Let me actually quickly update that. Oh, I did have it. Cool. You can type explanation exclamation point notes, and that should bring up the Mathcha.io page that I'm using as kind of the template for what I'm going to discuss. Also, can you yap about trigonometry too when you have the time? Yeah, I'll see what I can do. I don't think it'll fit into this lesson very well, but yeah, I mean, I can certainly take some questions at the end of this, I guess. Um, but yeah, so let's go ahead and get started here. Let me go ahead and adjust my model. Oh, also, this is a slightly newer model. You like my hat? I was trying to think. I wanted to make something a little bit, I guess, school and study related. Trying to find free assets on Unity. This was the best I could come up with. I don't know. Maybe I'll add on to this hat or something later on. Yeah, something like that. I'll just see a size as needed. Okay, let's get started here. Bam. Transfinite numbers, or how to count past infinity. I do apologize. This is not a very original title. I kind of realized after making this that's how a lot of people tend to describe this topic, right? How to count past infinity. I actually want to play a Vsauce video at the end of this lesson, which is also happened to be called How to Count Past Infinity. So, again, sorry it's not very original. I don't think there's a better way of really describing the concept, though, because, I mean, the idea of counting past infinity in and of itself is kind of a weird idea, and it's definitely not intuitive. So, I mean, I even just jumped into this lesson with this whole new phrase that's probably not very intuitive either. What the hell is a transfinite number, right? I'm going to get into the description more, but basically, it's a number that comes after all finite numbers. So basically, you imagine kind of counting up through all numbers, and then you enter the transfinite numbers. So, kind of framing this all, I'm going to give a very brief description on some set theory terms to the best of my ability, and then I'll jump into kind of two types of transfinite numbers, the transfinite cardinals and the transfinite ordinals. Again, I'm not an expert on any of this at all, so if there's anyone watching this, either the live stream or I think I'm going to make this a YouTube video later, if anyone is watching this and they see something glaringly wrong with my explanation, please correct me. I want to learn as much as I want to teach as well. But yeah, with that, let's go ahead and get started here. So let's start with some terminology. I didn't include it because there's not a whole lot of context I could really add, but there's a branch of mathematics known as set theory. And that basically is theory and mathematics with what you can do with an object called a set, right? What is a set? It's some sort of object that contains various elements within it. And those elements tend to be things like numbers, other sets, you could include shapes in there, etc. So I want to kind of frame this discussion as imagine way back when, before we had any of this funky math, before we had arithmetic, algebra, calculus, trigonometry, etc., right? What is the very first math that ancient man and woman would have learned to use? It's probably counting, right? Someone goes out and they're going to maybe count some types of food or count some types of objects that they're collecting. It's very important that they know how to count because it helps kind of, one, understand how much of something they have, but two, maybe even divide it amongst their friends or their family or something, right? So, inadvertently, we as humans kind of came up with this idea of sets because we had to come up with this idea of saying how much of something we had, right? Say you go out and collect berries, you have 10 berries, that's a set of berries right there, right? And that set has a couple properties associated with it, right? There is a number of berries that you've collected, and you can organize it and label each berry in turn. And those are all things that you can do with mathematical sets as well. I included a couple examples here of a set. So this here, this 1, 2, just think of it as the set of the numbers 1 and 2. Very simple, very straightforward. Think of this set as the set of the number 1 as well as the set of the numbers 1 and 2. So you can have a set that contains both numbers and sets in themselves. And the math gets maybe a little bit wonky around here, but the whole point of it is kind of the same, right? You have a set that contains things. You can also have a set that just contains nothing, which is the empty set, and that actually has and that has its own role in mathematics as well. There is nothing in there, therefore it doesn't have any size, but it's still a set, right? It's the same idea as like having a count of. Think of having a count of like 0, right? You don't have anything. Like, maybe 0 is not that important of a concept to have at that time, but it's still not a bad way to have it as far as comparison goes. But the other piece that I wanted to go over here is that sets can also have an infinite number of elements in it. So let's take this funky z here. What the hell does that mean? Well, that's really just a set of all integers. So if you think back to your math class, what is an integer? Well, it's going to contain 0, it's going to contain 1, 2, 3, 4, all the way up in the direction of positive infinity, right? But it's not just going to contain that, because integers aren't just positive, they're also negative. So you'll probably have -1, you'll have -2, you'll have -3, and you can go the opposite way too, towards negative infinity. So this here is a set with an infinite size, right? It doesn't matter what the highest number you can think of in this set is. There's probably a number higher than that. It doesn't matter what the lowest number in this set is. There's a number lower than that. So, but that's okay, right? We still have a way of kind of constructing the set and describing what its elements are. This set is just as valid as any other set. Just because it has an infinite number of elements in it doesn't mean we can't still represent it in some way, right? So yeah, that's the definition of a set. A subset, this is more so used in reference to like some sort of other set. A subset is a set that's made up of elements from the set that is being compared to, right? So if you think of something like this right here, you have the set of the numbers 1 and 2. So if you had a set that just had the number 1 in it, 1 is an element that shows up in the set of 1 and 2. Therefore, the set of 1 is a subset of that, right? So as long as the elements in the set that's being compared to is present in the parent set or in the larger set, it's a subset. And I was just talking about the set of integers, right? The set of positive and negative variables here, or the set of positive negative numbers here. What in the xer is this, Hector? Yes, so getting here into the nitty-gritty of set definitions. Last chance to find the set. Yep, exactly. So yeah, as far as subsets go, I already kind of discussed this set of all integers right here. It includes 0, 1, 2, 3, 4, as well as -1, -2, -3. And that all is a subset of this funky letter Q. So what the hell is Q? It's the set of all rational numbers. And just to go ahead and kind of make that more clear here, math, BB, Q includes not just 0, 1, 2, or -1, or -2, but it also includes things like 1/2. It includes things like 3/4. It includes things like -1/12. Basically, it includes not just all whole numbers and negative whole numbers, but also all fractions and negative fractions. X is all rational numbers. Yes, exactly. So all rational numbers would be present in this set Q. So it should make sense then. If we're talking about subsets, how as long as the elements of one set are present in the set that it's being compared to, it's a subset. The integers would be a subset of rationals. Every integer is a rational number. You can think of every integer as something divided by 1, right? 2 divided by 1 evaluates to 2. It's a fraction, and you typically wouldn't write it as 2 divided by 1. You just write it as 2. But it's still a fraction. You could still write it as a ratio. Therefore, you can categorize it as a rational number. Okay. So we talked a little bit about how sets can compare to one another. Let's talk about properties of individual sets themselves. Yeah, the set term seems familiar since you got linear equations problems, and I get to answer 0, a set or no answer. Yep, exactly. So yeah, let's talk a little bit about this property of a set called cardinality. Basically, it's a really fancy way of saying the size or the number of elements in a set. And you typically denote it by this symbol here, this bar, set, bar. So a number that is used to describe the size of a set is also called a cardinal number. And I'm going to go over an example later on once I get through these definitions to kind of build some intuition for how that works. But yeah, cardinality, just think of it as the size, or think of it as the amount of elements in a set. That's really all it is. A power set is a very special type of set that's also kind of used in comparison to a reference set, same as subset. And the power set is specifically, and this is going to be a bit of a wordy answer, bear with me, the set of all subsets of a given set. That's a lot of times I said the word set. And I'll go over an example in just a little bit, right? But the whole purpose of this is that we're constructing basically the list of all sets that you can possibly build from the set that you provided. And I also want to point out here that it includes both the empty set and the original set. And that might not be as intuitive, but it is an important point as well. A set is always its own subset. So you will, whenever you're considering what possible subsets there are of a set, you can consider the original set as well. And that should make sense, right? Because the elements in a set are always going to show up in themselves, right? And now, power sets also have this really cool property where they always have a cardinality of 2 to the power of the cardinality of the original set. And again, I'll get to the example in just a bit. But that's a cool property that you can kind of hold on to. And that's also, not to jump too far ahead of myself, that's kind of a way we can use to construct bigger sets. Because the power set is always going to be bigger, essentially. Or it's either going to be equal to, or in most cases, it's going to be substantially bigger than the set you started off with. I've got 2 more terms to kind of go through here. These are going to be a little bit more difficult for me to explain. But the main kind of purpose of these is to talk about how the ordering in a set sometimes does matter. So the terms I want to go over are well-ordered. Yes, Seth, what's up? Take a water break here. Yes, this is all part of the foundations of math, and I'll expand on that a little bit. I don't have all of the different kind of like ground rules of this frame of math present in this lesson. I think that's a little bit too complex for a first stream. But yes, this is all part of like foundational understandings of math here, all part of the set theory. So yeah, with some sets, some of them will have this property that they're well-ordered, and there's a couple different ways you could describe how things are ordered. Well-ordered is kind of an important topic, and it's especially going to come up later on with my transfinite ordinals discussion. But if a set is well-ordered, then that means you can create a subset where in that subset, you always have a smallest element or a least element. And you could do that for every subset in the set. So that's a bit of a weird, wordy way of describing what well-ordered is. But just as an example here, right? If we have the set of 1, 2, 4, any combination of these numbers is going to have a smallest number, right? 1 is less than 2, 2 is less than 4, 1 is less than 4. It doesn't matter which subset I make of this, something is going to be the smallest. This integer set of all integers, is not well-ordered because there's always going to be an element smaller than the rest of them. Now, I do want to point out, and this is kind of a tricky thing, so maybe this wasn't the best set to describe here, but just because it shows up as not being well-ordered doesn't mean we can't properly order it. And I will get into that a little bit more later on in the lesson. But the important thing to note is that some sets you kind of have to force to be ordered in order for them to be considered well-ordered. By default, they're just not going to be well-ordered. And then another property of sets that are well-ordered, and maybe not even necessarily well-ordered, but just ordered in general, is that you can use what's called an ordinal number to kind of describe something else about the set. So an ordinal number is associated with the ordinality or the order type of a set. And it's sometimes denoted by the symbol here, this ORD operator on a set. This is a bit harder to describe, and the reason why it's so hard to describe is because for most sets, for finite sets, this is indistinguishable from the cardinality. You can think of it for finite sets as the position of the last element in the set. Basically, how many indices or indexes in the set do you need to label everything uniquely? So, not necessarily the same exact thing, not exactly the same thing as size, but very similar, at least in the finite space. What branches of math that benefit from here apart from functions? No, that's a very good question. I think you can. I was about to say that there's some benefits in terms of like the transfinite stuff where you can use it to describe like fast growing hierarchies and stuff. I would imagine like any math that involves you having to like label individual elements and kind of keep them together would benefit. I think group theory borrows a lot from set theory in terms of labeling. I would imagine you already mentioned functions that would benefit as well, since you can kind of pair individual elements with each other. Ideally, though, because this is like, again, not to jump too far ahead, because this is foundational, you could probably extrapolate this to any major branch of mathematics if you go far enough. Basically, anything that involves a relation between two sets of numbers, a domain and a range, that has its roots in set theory, specifically because of how an element in one set maps to another. Okay, so with all of that explanation out of the way, I'm going to go ahead and go over some examples here. Let me give myself some more space here. So let's go ahead and start with the basic set. 1, 2, 3. We'll go ahead and jump in here. So this is the set of the numbers 1, 2, 3. The cardinality of this hopefully should be pretty straightforward, right? What is the size of this set? How many elements are in this set? It's going to be 3. 1, 2, 3. Pretty straightforward. What about the ordinality? What about the order type of this set? Also happens to be 3. Again, this is a finite set, so it's not quite as important that we distinguish necessarily between cardinality and ordinality. Just need to know that for finite sets, these are the same. Let's get into something a bit more complicated. What about the power set? What are the subsets of 1, 2, 3? So we'll go ahead and start with the obvious ones, okay? The empty set and the set itself, 1, 2, 3. Now let's start with each individual element. How about a set of 1, a set of 2, and a set of 3? And then lastly, we'll go ahead and add each combination of 2 elements. Now, if there are 4 elements, we would also include each combination of 3 elements, but we don't have to do that. There's only 3 elements in the initial set. That's it. That's the power set. You could just, again, you can just think of it as any combination of those elements plus the empty set plus the original set. And there you go. You have your power set. Now let's ask what the cardinality is of that power set. Now keep in mind, there's 2 ways you can go about this. Remember when I said earlier that the cardinality of the power set is 2 to the cardinality of the original set, right? Well, we know the cardinality of the original set. Me when I blinked for 1 second in math class. How LeBron finite sets. Yeah. What sets do you think he found? He discovered all the infinite sets before any of us did. 2 to the 3, because the cardinality of S, the cardinality of the original set is 3. 2 to the 3rd power, that's 2 times 2 times 2, that's 8. Is there any practical example, or is this conceptual math? It's probably going to be mostly conceptual here, only because we're not really dealing with too much of the nitty-gritty. That's probably a good thing to kind of clarify here, right, is that so much of the math we do is kind of abstracted. Because this is all very foundational, it's not necessarily important to know all this to know how to do math, but it gives context, I think, to the math you do. It shows that there's a logical consistency in the math that you do. But if you just assume that the math you do, handed to you, works the way it does, you could probably skip a lot of this lesson. At least I would think so. So, yeah, the power set, the cardinality of the power set is 8, because 2 to the 3 is 8. But there's another way we can kind of prove that, right? 1, 2, 3, 4, 5, 6, 7, 8. Just count the elements, the power set, they should equal. Yep. So, very simple example of kind of the calculations you can do around a set. I just wanted to include that to kind of give you a little bit of familiarity with some of this terminology because these symbols will show up later in the lesson. Yeah, so kind of right. Yeah, it's 8 sets. Yeah, yeah, this one. At least this one happened to have 8. If we had a set of 4, it would be 16 sets in the power set. Okay, so Zap, what you were kind of getting at earlier, this is all part of a foundation of math, right? So there is a kind of larger discussion to be had here. I'm not going to go as deep into it right now. There is this field, or I guess this theory called zermelo-frankel set theory, which basically is 8 rules. Nice. Did you just notice the glow hat? Yeah. Yeah, I got a nice Unity asset that hopefully makes me look smart. Okay, so there are 8 rules, like 8 baseline rules in zermelo-frankel set theory. There's actually 9 rules if you consider this one extra rule called the axiom of choice, and they all make up ZFC. So I'm not going to go too deep into what those rules mean, but a couple examples of rules, right? Like, I just want to make a bullet point. Example, like the axiom of infinity. That basically just means an infinite set exists. That's a very simple, straightforward rule. All it really says is we're allowed to have sets that have infinite number of elements. There is no proof for this. This is an axiom. The whole purpose of having an axiom in math is that we assume it to be true. And because we assume it to be true, we can essentially we can essentially infer other ideas in math because of it. Unfortunately, sometimes, at least with a lot of math, there's not really... I'm trying to think of the best way to put it. With math, you kind of have to make some assumptions going into it, because math is only as good as, I think, the learnings that you can get from your initial starting points, right? We kind of have to believe that there's an infinite set that exists, because if not, we probably wouldn't even be able to describe what infinity looks like, at least in a mathematical sense, right? Let's see. I want to pull up at least one other rule. Let me see if I can. ZFC. I just want to make sure I I want to make sure I actually say a rule that exists before I say something that's actually not true. Okay, yeah. The existence of power sets is another axiom, right? The axiom of power set. I thought there was also an axiom that talked about comparing the cardinalities, but anyway, I'm getting ahead of myself here. I do want to do a lesson on ZFC at some point. I need to better understand it first myself. But the whole purpose of ZFC is that, and I want to kind of bring this all back home, right? ZFC is considered a foundational mathematical theory, which means these 9 rules, the 8 axioms of Zermelo-Frankel plus the axiom of choice, those 9 rules give you all of mathematics as we know it. Arithmetic, geometry, algebra, calculus, trigonometry. All of those can be inferred and derived logically from these 9 rules. And I think that, I find that extremely powerful, right? The fact that for the longest time, a lot of these branches of mathematics were considered kind of separate. Like maybe there were some threads that kind of stitch them together, right? Like, of course, you need some arithmetic in order to use calculus, right? But I think the question of what kind of follows from what wasn't well understood, right? Some attempts were made in terms of showing how logically you can get from one point to another, but really, ZFC is the most powerful tool we have in that regard. The mathematicians Zermelo-Frankel, those aren't the only ones. Georg Cantor was another one. He's actually the one who kind of really worked on the theories around infinity. Um, yeah, those mathematicians, their work to come up with this foundation, this zermelo-frankel, it ties everything together. You can derive pretty much anything that you would learn in most like elementary, middle, high school, college courses. You're probably going to study. It comes from ZFC, logically. Okay, there's a bigger discussion to be had there. I think it's really fascinating. I need to read up on it before I can really go more into detail on it. But let's get into the next topic here. Let's actually start talking about what the hell transfinite numbers are. Okay? So, let me ask you a question here, right? The set of all natural numbers, the set of all counting numbers, right? Like I said towards the beginning, the earliest mathematics people probably figured out how to do was counting, right? And that was necessary because maybe they needed to keep track of food supplies or keep track of objects they were collecting. So you assign each of your items a number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You could go on forever, right? You can go way towards infinity. Because of the axiom of infinity, I can say, let there be an infinite set of these counting numbers. What's the cardinality of that set? So maybe your first thought when you hear a question like this is, can we even do that? Does that actually make any sense for us to take the cardinality of a set? And this kind of that may be more of a philosophical question a little bit. And I want to answer it with two things. One, what even is infinity, right? Infinity, for the most part, is not something that exists in our world. It's something that's so outside of our grasp as humans that we can't really put a finger on very well, right? It might not even be unreasonable to call it a direction, right? Maybe you think back to your algebra classes or something, like when you're graphing 1 over x, and you see as the closer you get to 0, the farther up and up and up the graph goes towards infinity, right? You know it's going there. It's never going to touch infinity, but it's going to get closer and closer and closer and closer, right? We're just not going to be around to see when it actually hits it, because there's nothing really to hit, right? The idea is that it just keeps going onward forever, right? Infinity has a little bit of a different idea in set theory. So the second piece I kind of want to go over is, sounds like an asymptote? Yeah, exactly. And that's how most of us will learn what infinity is through asymptotes or through just adding numbers or watching as functions just shoot off to infinity, never to be seen again. I want to kind of point out here, though, that so much of math is kind of just based on not really worrying about whether you can do something and just seeing what happens when you do it anyway. And maybe that's not a very good answer. I'm an engineer in my job, and part of what I'll do sometimes is if I'm trying to solve a really complicated problem, I break it up into two parts. The first part is, what is the correct behavior? And the second part is, if the correct behavior is realized, what does that mean? So there's a little bit of what if we force the correct condition in this situation, right? What if everything is working properly? What can we learn from that? And then it's just a matter of kind of figuring out how to get it to work properly. And that's a little bit of what happens in math as well. We know for a fact we can write sets of infinite size, right? We have a whole axiom that dominates it. We know we can take the size of finite sets. Surely, we could at least try to assign some sort of number to this set. What would that number look like? This is where we get into our first major definition of this section and the title of this whole presentation. Transfinite numbers, larger than any finite number. The cardinality of the set of all natural numbers is a transfinite number. And more importantly, It's countably infinite. Countably infinite is just a very fancy way of saying that we can reach it by counting upwards. 0, 1, 2, 3, 4, 5. Keep going off in that positive direction. That is a countably infinite set. And I'm going to get more into what that actually means later on here. So let's actually assign some sort of number to it. The number that set theorists have assigned to the cardinality of the natural numbers is this cool symbol here, which is also called Aleph null. You could also call it Aleph 0. You could call it Aleph naught. I like Aleph null, personally. So, again, right now we're kind of in the state where, like, let's assume we can assign a number to this cardinality, right? Let's assume that we can say what the size of the set is. What kind of properties does this number have? Well, for starters, it's going to be larger than any individual member of the set of natural numbers. Because again, your set of natural numbers goes on forever. Think of the biggest number you can. I can think of a number bigger than that, right? You can think of a number bigger than that. Aleph null is going to be bigger than any of those. And that's kind of a weird thing to say, because that implies maybe that if you go far enough along the set of natural numbers, you'll get there. So again, I want to kind of bring you back to the definition of transfinite. It's larger than any finite number. So there's not really... You're not really ever going to reach this number just by continuously adding 1, right? This is something that kind of transcends all of that. It's way beyond anything in the finite realm. Again, we as humans are kind of bad at imagining what infinity looks like, but this is kind of an attempt for us to do so, right? One really weird and kind of disturbing side effect, too, of infinity, or at least of Aleph null, is that for any cardinal number that's less than or equal to Aleph null, adding to Aleph null and multiplying by Aleph null doesn't actually change the size. Infinity plus 1 is still infinity. Technically, we could run out of names for large numbers. Yeah, I mean, I would argue that there's probably not enough combinations of letters in the English alphabet to be able to properly explain numbers. There's certainly not enough symbols that can properly explain the size of numbers, nor is there space in the universe to write down the largest of numbers. Like numbers at 10 to the 75 plus, yeah. I think people have come up with creative numbers for them. I don't know at what point they've stopped, you know? Because we have things like, what, billions, trillions, quadrillions, quintillions, sextillions, septillion, octillion. We have Google, we have Googleplex. It's gotta stop at some point. At some point, they just stick to scientific notation, like you're doing, right? 10 to the 75. But even if we were to come up with some words to describe it, I don't know. I would agree we would run out at some point. Yeah. So Aleph null doesn't play nice with other numbers. If you add 1 to it, it doesn't change the value. And again, 1 plus infinity is still infinity, right? So that's a tough thing, I think, to wrap your head around, but at the same time, you're already considering something way off, far off in infinity land. I think it makes sense that a single number isn't really going to change the value all that much. Now, probably the most interesting side effect of Aleph null, and kind of coming back to this idea of what's countably infinite, all sets whose elements can be individually mapped to a unique element in the natural numbers also have a cardinality of Aleph null. So this is called a bijection, when you have two sets that map exactly to each other. Now, this is very disturbing as a concept, because what it implies is that the set of all even numbers, odd numbers, prime numbers, integers, rational numbers, algebraic numbers, they all have Aleph null elements in them. Now that's a really scary concept, in my opinion. How the hell are there the same number of even numbers as natural numbers? Like, that's a really disturbing thought, I think. So let's explore that a little bit, right? Let's start off with something simple, right? Let's start off with math BB. Let's start off with just comparing the even numbers to the odd numbers, right? The first thing you learn in college. So let's say, before your professor decides to throw octal, binary, decimal, hexadecimal, oh yeah, you learn about, and the rabbit hole math I'm in. And then odd is 1, 3, 5, 7, 9. Okay. So we have two sets here. The set of even numbers and the set of odd numbers. I think it should be a little bit straightforward that these sets are gonna be the same size, right? I mean, for every time you have if you don't have enough odd numbers, you just add 1 to the biggest even number and you have a new odd number, right? And that's kind of what the whole bijection mapping really shows. I might get my set theory notation wrong here, so I do apologize in advance. But another way you can think of the set of, like, odd numbers is that it's all y, such that for every x, and there's your XER notation, by the way. I'll just do XEN, though. For every element of the natural numbers, y is going to be x plus 1, right? And this is actually going to be the set of even numbers, my bad. Not trying to confuse y'all. Okay. We take every element in the set of even numbers, we add 1 to it. Congrats, you just made the set of all odd numbers. And you do that forever. So because you can do that, that's enough for us to prove that the set of even and odd numbers have the same size to them. Right? Big sets. Now let's do the other disturbing thing, right? Let's do the set of all natural numbers and how these compare. So let's write the set of all even numbers in a slightly different way. It's also going to be the set of all y, but this time we're going to look at the set of all natural numbers. Every element of the natural numbers. Bam. I take a natural number, I multiply it by 2, I get an even number. Right? 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. The set of all even numbers has the same size as the set of all natural numbers. And I don't think that is definitely not obvious, I think, because you think, hey, there's only half as many even numbers as there are as total numbers, right? Because the other half is odd. But keep in mind, these sets go on forever. These sets are infinitely large. I think what a lot of mathematicians will say is that these sets are less dense compared to the natural numbers, but that doesn't actually change the size when you have all of infinity to go through. And you can have similar rationales for other sets of countably infinite numbers. Remember early on when I said that the integers were not well ordered? Well, it turns out if you can find a way to order them, you can prove that they have countably infinite elements in them. Rational numbers, algebraic numbers are kind of all fractions, all integers, all positive, negative numbers, but they also include things like the square root of 2 or the square root of 3. Basically, any solution to a polynomial equation fits in the algebraic numbers. Those are also countable. Those are all countably infinite. Okay. I just got done talking about all of these sets and how it's wild that they all happen to have Aleph null elements in them, right? So let me ask you something else. What about the reals? Does the cardinality of the real numbers equal the cardinality of the naturals? So what is a real number? Well, it includes everything we've gone over so far. It includes your natural counting numbers. It includes your negative numbers. It includes your fractions. But it also includes, excuse me, it includes all irrational numbers as well. Pi is a real number. E is a real number. Square root of 2, yeah, it's algebraic, but it's also a real number. There's a lot of real numbers out there. And keep in mind, the whole thing with irrational numbers is that you really can't write them down. I'm sure you've heard everyone talking about, oh, we found like the trillionth digit of pi or something, right? That's something someone had to work out because there's not an easy way to represent pi other than an approximation, right? Don't get me wrong, pi does have a value. It's just that we as humans can only calculate it to specific precisions and have to put effort into figuring out how to get as precise as we want, right? So, there's a lot of real numbers out there. But, again, as long as we can find a mapping between the set of real numbers and the set of natural numbers, maybe they're the same size, right? I want to go ahead and do kind of a live exercise here of your Cantor's diagonalization proof. And this is an incredibly powerful proof. Your Cantor is also responsible for a lot of these kind of notations about infinity as well. And he was also, as far as I understand, very controversial for his time. A lot of people didn't like that his talks of infinity seemed to spit in the face of God, which I find incredibly fascinating. But yeah, we're going to go ahead and try out mapping the real numbers to the natural numbers. So I'm going to start off. Let's go ahead and try to write down all positive numbers less than 1. But I'm going to give it a bit of a twist. I'm going to use binary notation in the decimals. You will see why, I promise. So let's say for the first number, 0. What do we want to do here? How about we make this all ones? It'll go on forever, right? Let's go ahead and write down another number. Maybe this one can be all zeros. Let's write down another number. How about 1010? And maybe that repeats to infinity. And then let's write down 1000. I'm going to be doing this a lot, right? So you get the general idea, right? We can write these numbers to whatever precision we want. They're going to have an infinite number of terms anyway. But I'm also going to have an infinite number of numbers here, right? You can just imagine that I'm going to keep doing this forever and ever and ever. I'm going to keep writing down these numbers. And then theoretically, I should have written down every single number between 0 and 1, right? After I've gone through an infinite number of steps, I will have every number. Okay? I want to write a new number now. And not to jump too far ahead of myself, I'm going to give this a very unique name. I'm going to call this S omega. Omega just means it comes next, essentially. Don't want to spoil myself here. Now, I'm going to write this number in a very specific way, a very tricky way. At every position, I'm actually going to look at a number, at the number of that index, and I'm going to take that index and flip it. So for the first position, I'm going to look at my first number, which is a 1, and I'm going to flip it. It's a 0 now. In my second number, I'm going to look at the second position, flip that. So in my new number, the second position is a 1. I'm going to look up at my third number. Third position is a 1. Let's flip it. My third position in my new number is a 0. And finally, the fourth number. the fourth position is a 0, flip it, it's now a 1 in my number. And I'm going to do that for all of the numbers that I wrote down here. Here's the problem. This number here, by definition, is different from every other number in this set. This number is not going to show up at all in the infinite number of numbers I've written down here, because it's going to differ by at least one position. This is the power, and this might seem like a very simple, even kind of stupid approach to this, but this proof right here is so powerful because it proves that some infinities are bigger than other infinities. It proves that the set of real numbers is much, 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 much bigger than the set of natural numbers. And we have a word to describe sets like this. We call it uncountably infinite. It cannot be reached by counting upwards, and there is no mapping, there is no bijection with the set of natural numbers. It doesn't matter how crafty you get. It doesn't matter how well you think you can label your numbers. You will never be able to do a one-to-one mapping of all the real numbers with the set of natural numbers, ever. So, now that we've identified that there are some numbers that are uncountably infinite, let's talk about what they actually look like. What does an uncountably infinite cardinal look like? Well, let's just start off with kind of a simple by the definition type deal. When we wrote down Aleph null, that subscript is just an index. The way that the Aleph numbers are constructed, if we increase that subscript, we've come up with a bigger infinity. And you might reasonably ask yourself, how much bigger are those infinities, or how do they relate to each other? And I'm sorry to say, there's not a very good mapping as far as they go, but by definition, Aleph 1 is going to be bigger than Aleph null, Aleph 2 is going to be bigger than Aleph 1, and so on and so forth. And then there are some explanations for what they represent. I think I recently saw a number file video where they were talking about how Aleph 1 represents like some combinations of like elements in Aleph null. It's not very easy for me to explain. Maybe I'll be able to come up with a better explanation in the next lesson. But all you have to really know is that if we wanted to generate bigger numbers, we could just increase that subscript. The Alephs are like robust enough that we can do that. But I also want you to think back to when I was talking about power sets, and how power sets are a way of just generating bigger sets in general, right? The power sets of infinite sets are going to be uncountably infinite, because by definition, the power set of the natural numbers, that size is going to be greater than Aleph null. And again, maybe you're kind of asking, can we even do that? Well, this might even be more justifiable, right? Because we have the axiom of infinity, we have the axiom of power sets, we can have a power set of an infinite set. And if that's the case, and we can assign cardinality to the size of the natural numbers, certainly we could talk about the size of the power set as well. By definition, that size is going to be much bigger than Aleph null. So let me go back to the question of how much bigger, right? Maybe you're going to ask yourself, well, if the size of the natural numbers is Aleph null, does that mean the size of the real numbers is Aleph 1? It's a very good question. And it's actually one of the biggest unanswered questions in the past century in math. It's a major unanswered question because we don't really understand where Aleph 1 sits compared to the size of the real numbers. We don't know if Aleph 1 equals the size of the reals. It could be bigger. The size of the reals could be much, much bigger than Aleph 1. We just don't know. What we do know, and it is provable, is that 2 to the Aleph null is the size of the reals. There's a proof that I'm not very well versed in. Maybe I can include it in a future video. But this is provable. The size of the reals is equal to 2 to the olive null, which is kind of neat, in my opinion. Maybe you've heard this terminology called the continuum hypothesis, which basically states that 2 to the olive null does equal olive 1. That's a hypothesis, right? This is something that some mathematicians believe is possible. And there's some kind of interesting qualities to this hypothesis. One, it asserts that there is no cardinality between that of the naturals and the reals, right? Because the continuum basically means that you're going continuously from one cardinality, the naturals, to the next one, the reals. And maybe that feels a little bit intuitive. I mean, we already know we can't get to cardinalities easily, right? We can't just keep adding 1 to the set of... we can't keep adding 1 to olive null in order to get to olive 1. Now here's the frightening part, though, about the continuum hypothesis. And this is what we understand from zermelo-frankel set theory, as well as the axiom of choice. There is no way to prove or disprove the continuum hypothesis based on this understanding of math. And it was actually proven that you cannot prove or disprove continuum hypothesis. Somehow, our mathematics is robust enough to tell us one way or another that we can't prove this, but it can't actually prove it. So, at this point, you could potentially use other variants of mathematics to potentially prove it. I've heard about this axiom of constructibility that supposedly implies both the axiom of choice and the continuum hypothesis. But it's also like, what's the point, right? Zermelo-Frankel set theory has, like, use cases outside of just talking about cool infinite numbers, right? It's not necessarily important to us whether the continuum hypothesis is or is not true. Maybe some people are really interested to know. I'd be interested to know if there's an answer, but we're probably never going to find it. I'll just end this section by saying that there are other examples of infinite cardinals. There's a numbering system called the Beth numbers, which have a very similar idea. Basically, the idea is that Beth null is the same as Aleph null, and every single Beth of n plus 1 is the same as 2 to the cardinality of Beth n. So this is basically like, what if the continuum hypothesis is true, and it's also true for every subsequent, like, infinity, essentially? What if it's always true that the cardinality of the next major transfinite number, or the next major transfinite uncountable set, is also going to be 2 to the previous set, right? I don't know. I don't know too many applications for this numbering system, but there are other ways of describing infinite numbers besides Alephs. Aleph just happens to be the most popular, and it also creates the most questions, I think, because it doesn't just assume that this relation always holds. Okay, we spent a lot of time talking about transfinite cardinal numbers. Now I want to switch gears into something that's a little bit weirder, called the transfinite ordinal numbers. So I want to open up this section by saying we can't really come up with larger cardinal numbers without using Aleph numbers and power sets, or Beth numbers, if that's what you want to use. But order type does allow us to kind of consider numbers in a slightly different way, such that we can model numbers that come after all other finite numbers. So again, I want to make this distinction here, right? We've been talking about numbers that are by definition greater than everything in the finite space. What if we took a step back and thought, what if we just are concerned not about whether or not something is greater, but about ordering them such that the next thing that happens has to come after all finite numbers. I don't think that's a very intuitive thing to think about, but remember, part of the reasons why you might want to put things in sets is to organize things in a certain order, right? You might want to be able to label each item clearly. If you're going to add items to your set, you need to be able to label each subsequent item that comes after it. So I want to give you two terms to start off with. A successor ordinal is an ordinal number that's reachable from a previous one. So you could actually think of, again, we were talking previously about how for finite sets, ordinality is the same as cardinality. That means for finite numbers, cardinal numbers and ordinal numbers are the same, right? 2 is both a cardinal number and an ordinal number. And it's a successor ordinal because it comes after 1, which is also a successor ordinal. So then, we have another term here called limit ordinal, which means they cannot be reached by a successor. And I will very quickly get into what that means in just a second here, once I go over this next explanation, this transfinite recursion. So, we've been kind of hinting at this a little bit. Transfinite recursion. The basic idea is you're doing something an infinite number of times that brings you, the expectation is that it gets you to the point you want to get, right? So we've already kind of seen that in Aleph Null, right? You can only get to Aleph Null if you start off with a set that has a countably infinite number of elements in it, right? You will never be able to add 1 to itself enough times to get to Aleph Null. You'll just get there by virtue of the fact that you have a countably infinite set. Well, in ordinal land, when you're dealing with ordinal numbers, the same thing happens, right? You could do something an infinite enough times to get to the point where you've reached some sort of ordinal in the future. So let's quickly jump into an example of that. Remember when I previously asked what the cardinality of the natural numbers is, and that's Aleph Null. If I ask you what the ordinality is, your first thought might be that that's also Aleph Null. But I want you to consider a slightly different way of answering that. What if, instead of saying, this is the total size of the set we're working with, how do we say what the next element in that set is going to be if we were to add to it? And what I want to kind of point out, and maybe the hardest thing to stress here, is that this is different than just adding 1 to the set. This is saying we have an extra element of the set. We need to consider this an extra element. It's outside of the natural numbers. So let's think of it as what the next number that comes after all the finite numbers is. Think of it not as necessarily being larger, just it comes next. Once you've gone through all the finite numbers, omega is the next number you end up with. So this is kind of going to lead us to another set of wonky mathematics here, right? I just got done telling you, oh, well, if you do math on Aleph numbers, it's just going to get consumed into it, right? And the only way to get to the next one is by adding 1 to the subscript, right? You can do arithmetic with ordinals. You can treat them as different numbers. You just kind of have to be a little bit creative of how you do it. And again, your arithmetic, your adding of ordinal numbers, is just going to tell you what position you are on in the number line. It's not necessarily telling you what's bigger than these numbers. It's just telling you what comes next. So let's jump into this, right? What comes after omega? Well, you could think of it as the ordinality of the set of natural numbers union the set containing omega in it, which is just a really fancy way of saying, if I have the set of natural numbers and omega, what's the next number I need? Well, it's going to be omega plus 1. So addition here is kind of a stand-in for the number that comes next. It's not the same traditional addition that we're used to. Just think of it more as like a notation. You can call it addition if you want, but it's more notational here. So let's start trying to build bigger and bigger ordinals with this. Imagine taking every element of the natural numbers and adding it to omega. What do you think the last element of the set is going to be? So there's a function called supremum, which is used a lot in like ordinal arithmetic and ordinal analysis. Basically, it's the result that you get from iterating a process enough times. This, again, transfinite recursion. Doing it enough times, and then you get this least upper bound. So basically, it's going to be the limit as you do this transfinite recursion. So let's think about that, right? Omega plus 1, omega plus 2, omega plus 3, plus 4, plus 5, plus 6. You do that enough times, what are you going to get? Well, it's going to be omega plus something, right? I mean, we're just doing addition here. But if you go on enough times, it's going to be omega plus omega. And you can write this in a couple different ways. I've seen it written as 2 times omega. I've seen it written as omega times 2. I personally like this notation because it kind of speaks to the very odd nature of ordinal arithmetic. And it'll help you not get confused and think that this is arithmetic in the same way that you would finite numbers. But yeah, if you do this process enough times, the next thing you'll get is omega 2. Now, omega 2 is an example of another limit ordinal. Omega is a limit ordinal. Omega 2 is a limit ordinal. You will only reach it after doing transfinite recursion. So let's go ahead and go over a couple more examples, right? So let's talk about... I don't want to jump ahead too far here. Let's talk about the supremum of maybe omega 2, omega 3, omega 4, there we go, etc. What do we think this value is going to be? This time, instead of adding each number to omega, or each natural number to omega, we're multiplying each natural number by omega. We do this enough times, we're going to get omega times omega, or omega squared. There's our new limit ordinal. Let's do it again. What if we did omega squared, omega to the third, omega to the fourth? What if we do that enough times? You can probably figure out what pattern we're going for right now, right? I think it should be fairly straightforward. Basically, we just replace whatever is stacking as far as the natural numbers go with omega. So we're going to get omega to the omega power. I have some bad news, y'all. We don't have to stop there. We can keep going. So let's go ahead and do that. Maybe just one more time. Omega to the omega. Omega to the omega. To the omega. Now, it might not exactly be obvious what's happening here. Or maybe it is, right? It's a tower of omegas. We're just adding a new one onto the tower. The answer is going to be absurd. It's going to be omega to the 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 omega. Forever. Well, that's pretty fucking wacky looking, right? It's literally a stack of omegas. An infinite stack of omegas, mind you. I mean, it's a limit ordinal, but something different has happened here, right? This is actually as far as our mathematical notation goes here, right? Like, there's not really a better way of describing what's happening here than the way I've written it out right here, right? Like, sure, I don't know how many of you got this far in your mathematics classes, right? You have multiplication, you have exponentiation. There's something called tetration and pentation, which basically are faster ways of creating bigger numbers. But what I've written here basically transcends all of that. We can't really write this in a more efficient way, at least just doing this kind of stacked notation, right? Here's the thing, though. We're not done yet. This isn't the biggest ordinal we can make, not by a long shot. So I want you to think about another way that we can write this. And maybe some of those that have done some of these kind of trickier types of math problems would recognize is that when you have an infinite recursion like this, you can simplify it by just using some sort of variable to stand in. So let's rewrite this as a limit ordinal that we're going to call alpha, where alpha is equal to omega to the alpha power. And you'll notice that if you put omega to the omega to the omega to the omega in for alpha, you get the same on both sides. So I've heard this called a fixed point. It's again only reachable by transfinite recursion, but it represents, I think, something a little different in our setup here, right? Again, we only got here because we broke what we're capable of doing with the mathematics that we have. So this limit is called epsilon naught. And you can think of it in a couple different ways, right? Omega to the epsilon naught, or omega to the omega to the omega to the omega, right? All it is just the next ordinal that comes after. After we've done this activity of taking all these omegas to the power of each other, do we get to this epsilon naught. But again, that 0 is just a subscript. We can get to bigger epsilon numbers if we want as well. This epsilon to the n plus 1 is considered the supremum of this set here. Epsilon naught to the epsilon naught to the epsilon naught. And we can keep doing this forever, you know, why not? So I'll spend just a little bit more time here. I won't harp on it too much, but let's think about some more bigger numbers that we can get to, right? So maybe we can do something like epsilon. Oop, I don't want to use that epsilon. There we go. Epsilon naught, epsilon 1, epsilon 2. Well, that's just going to be epsilon omega, right? What about epsilon omega, epsilon omega to the omega, epsilon omega to the omega to the omega, and so on and so forth, right? Well, that's going to give us epsilon to the epsilon naught. And you can probably see what direction we're going in now, right? You can really just get very weird with these, right? You can have, like, epsilon naught, and then epsilon naught, and then epsilon naught. And that just goes on forever. So you end up with this weird stack of epsilons that just kind of goes on forever in the subscript. What the hell is that? Well, we have a number for this too. We call this zeta naught. And just like that, we found a new ordinal, a new limit ordinal. Well, guess what? Turns out, you could keep doing the same old trick as well. because epsilon naught, or sorry, zeta naught rather, and zeta zeta naught, and zeta 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 naught. Well, that's a new number as well. We call that eta naught. I've already spent several minutes typing all this out. I don't need you to watch me keep doing this, but maybe you're thinking to yourself, Rad, is this the only way for us to make limit ordinals? Are we just going to sit here typing these weird stacks of numbers for the rest of time? We could. I mean, we certainly could keep doing that, and you will get bigger and bigger limit ordinals doing that. But that's kind of boring, isn't it? And I don't think that really addresses the reality of ordinals in general, right? At least of the transfinite nature of them. Because keep in mind, we have uncountably infinite cardinal numbers. Aleph 1 can never be reached by just adding 1 continuously, right? The same goes for ordinals. We can't just keep doing this type of recursion forever. Now, what I will say is that we got some hints of that early on. There is a number called the Pfefferman-Schuit ordinal, which is this gamma naught. We can't reach Pfefferman-Schuit doing this method. We can't just keep making bigger and bigger, wackier subscripts here. There are some functions out there that model this properly. There's a whole class of functions called the Veblen functions, which basically have a very simple form here. This is kind of the most basic definition of Veblen functions. This phi alpha is equal to omega alpha, where alpha is some sort of ordinal. It's either a limit ordinal or a successor. Doesn't matter. Could use whatever. But you'll notice here in the second line that we have some numbers here. Oh, I should delete that. There we go. We have some numbers here where if I, instead of using 1, I use 2 variable, or use 2 value arguments here in this, rather, excuse me, we get epsilon naught. And if I use 1, 1, I get epsilon 1. And if I use 2, 0, that gives us zeta naught. Black slow internet speed. You doing all right, buddy? Apparently your ISP is having router issues. Oh, sorry to hear that. Yeah. It's okay. I'm getting kind of close to at least the end of this section here. You swear you were having 18 to 25 upload this morning. Yeah, I hope it gets resolved for you. That always sucks. Yeah, just to wrap up this section here. Veblen functions, which I am not going to get too much deeper in. This is more so just to show you that you can do similar type of supremum, like limiting modeling, right? If I just take the phi of the phi of the phi of the phi, you'll watch the VOD later? Sounds good. Thank you so much. I appreciate your interest in this. I know that this is getting a little bit heady, and I am not doing the best job of explaining it, but I do appreciate that you're interested in learning this. Yeah, I'd love to do more videos like this. But yeah, all of this to say, you could technically get to larger ordinals like Pfefferman-Schuit doing this kind of method, but it involves you having to like come up with alternate ways of doing it. And that's all I'm trying to say. You'll never reach Pfefferman-Schuit by doing this kind of recursive limiting and getting to these kinds of like doing this like epsilon to the epsilon to the epsilon or zeta to the zeta to zeta. You're never going to get that. You grew up with making math practical, but having concepts explained and how and why it works helps. Yeah, I think so too. And I know we've talked about this previously, but the cool thing with math is that sometimes someone will come up with a way of modeling or conceptualizing something that doesn't have an obvious practical application, but then someone will figure out one. I think this is a very interesting field where even the applications are not super duper like obvious. Like even explaining why you can't divide by 0 and why to the 0 is 1. Yeah, yeah, exactly. So that there is a use for being able to explain that, right? It says something about the nature of numbers and how they work with each other, right? But yeah, um, Pfefferman shoot. Basically, the whole point of it is it's a really big honking ordinal. You can't really get to it easily. You can model ways to get to it. Veblen functions is one way, and hell, you can even just keep modeling Veblen functions as getting bigger and bigger and bigger. This is going to be way bigger than Pfefferman shoot. So much bigger than Pfefferman shoot. So it's not really a matter of like, oh, we can always make a bigger ordinal, right? Now here's the thing. Here is the major kicker. All of these ordinals pale in comparison to the first uncountably infinite ordinal, omega 1, or capital Omega. Let that sink in. Every single ordinal I have gone over so far, doing this transfinite recursion, doing this supremum of an infinite number of steps, stacked omegas, stacked epsilons, stacked zetas, stacked etas, Pfefferman shoot. Omega 1 comes way after all of those. By definition, it is uncountably infinite. So where does this actually show up? Where does Omega 1 show up? Well, think back to Aleph Null. You know how Aleph 1 is bigger than Aleph Null? Well, if you have a set that has cardinality of Aleph 1, then the ordinality of that set is going to be Omega 1. That's right. Everything we've talked about on the number line happens between Aleph Null and Aleph 1. Infinity is weird. It's hard to explain. It's hard to conceptualize. It's hard to understand just how big infinity is and how these numbers that we can only hope of being able to model and talk about with reference to other bigger numbers. And the thing is, you could just keep doing this forever, right? Why not? Let's just increase the subscript of omega. Omega 2, omega omega, omega epsilon naught, omega Pfefferman shoot, omega 1, omega 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 omega. Sure, we'll just keep making bigger numbers. Why not? This is all just getting rather silly, right? I mean, we're now talking about things that we can't even properly really define here. I could probably just come up with a new symbol and say, oh, it's bigger than everything. I was watching a number file video not that long ago where someone proposed there is a number called absolute infinity, which uses like the last letter of the Hebrew alphabet. I don't know how I feel about that, but how do we know there's just not something bigger? Our minds were not really designed to conceptualize infinity. So to that, I kind of pivot away from all of this talk about bigger and bigger ordinals, and I ask, how is any of this useful? And Zaf, you were kind of asking a little bit about that as well, right? There's two places where, to my understanding, knowing how these ordinals stack is actually useful. And one of these, I actually do want to give an in-depth explanation as for a future video. Fast-growing hierarchies. It's a way of being able to model the speed at which certain functions grow. If any of you have ever heard about the function tree, then you'll probably know that tree of 1 is 1, tree of 2 is 3, and tree of 3 is bigger than anything we can ever hope to imagine. Tree of 3 is a monster. We can't write it down. I don't think we even know any of the digits of tree 3. I'm honestly not sure. And not only that, we've actually proven, from what I understand, that we will never be able to write down tree of 3. Exponents? Oh, it's more than just exponents. It's exponents stacked on exponents stacked on exponents. It's bigger than anything. At least with something like Graham's number, we can at least come up with a formula for like visualizing what it looks like. I don't think that easily exists for tree 3. Is this how exponents or subscripts log-like came to be? They probably were developed before we got to this point, honestly. I'm gonna go ahead and stop the sound here. I'm actually pretty much done with this section, so I'll stop the background music for now. I would expect exponents and subscripts probably predated a lot of this by a while. I think, if anything, exponents and subscripts were probably used to model these really big functions and these fast-growing functions. I think just the important thing to note here is that we do have these functions that are these functions that we've conceptualized. We have ways of describing how to build these functions, but we don't actually have a way of really evaluating what this means. If you look up the definition of what the tree function is, and then try to evaluate it at 3, the number you get out of it is so big that not only does it break our understanding of how big numbers can be, it breaks our understanding of how fast functions can grow, right? I'm sure you probably learned in school, right, that 2 to the x grows faster than x squared. Tree to the x grows faster than anything you will ever deal with in your life, by a long shot. And that's not even the fastest growing function. That's probably at least the one that the application that I'm the most familiar with. I've also heard that proof theory uses ordinals to describe the consistency between the proofs, but I don't know if I could say necessarily how well it does it. I certainly wasn't able to come up with examples prior to this. I'll make a note of 3 to the x. Yeah, so 3 to the x would also be faster growing than 2 to the x. X to the x would be faster growing than all of those. Basically, you have ways of being able to model how fast these functions are growing in different ways. So yeah, proof theory, I'm going to leave that as an exercise to all you. I'd be interested in learning more about proof theory. I don't know anything about it. But that seems to be another case where understanding ordinals might actually help you. And that mostly concludes the lesson I wanted to go over. I actually wanted to potentially spend the rest of this time going over a YouTube video that kind of spurred my interest in this. Maybe adding a little bit of commentary, and maybe also acting as a bit of a review for all of this too, right? So I probably won't include this in the YouTube video itself, just because, again, it's referencing another YouTube video. How would LeBron use the sets he found to make that basketball shot? He could probably use it to make a set of, I don't know, vectors or something like that. All the possible directions he could shoot the ball and all the probabilities that they'd probably have in sinking the ball in the net. Yeah, I'd imagine LeBron has a pretty strong set theory background if he's able to visualize, I don't know, the vectors of his shots like that. So, yeah, good on LeBron. So, with that, I'm going to go ahead and pivot to the video, I think. So, let me go ahead and get that pulled up here. I'll go ahead and probably interrupt the video a little bit to kind of tie some of these things back into the main lesson. Would LeBron-Stantonopol last 10 centuries? It could if LeBron learns more than just set theory and can learn how to extrapolate economics and shit from all of the math, I guess. Microsoft Edge and Microsoft Edge. If the video sound is his shot impacted historical legacy. Yep. If the sound is too loud, please feel free to let me know. But yeah, let's go ahead and jump this video. Like I said, I'm going to pause it from time to time so I can kind of add some extra commentary here. I really like this video. Again, it's also called How to Count Past Infinity. It's by Vsauce. Great video. Let's dive in.
Hey Vsauce, Michael here. What is the biggest number you can think of? A Google? A Googleplex? A millinillion olplex? Well, in reality, the biggest number is 40. Covering more than 12,000 square meters of Earth, this 40, made out of strategically planted trees in Russia, is larger than the battalion markers on Signal Hill in Calgary, the 6 found on the Fauvin badges in England, even the mile of pi Brady unrolled on Numberphile.
Just want to jump in here and say, I love how Vsauce in his videos will always pivot in his explanations to some random factoid that may or may not necessarily be super relevant to the rest of the video. Because, yeah, I mean, I certainly didn't know that that number 40 was the largest, like, area of a number. Yeah, what kind of cooking is this? We're cooking with math. We're cooking with math.
40 is the biggest number on Earth in terms of surface area. But in terms of amount of things, which is normally what we mean by a number being big, 40 probably isn't the biggest. For example,
when the professor tells you the exam is based off what we learned, the exam. Yep, this is the final level of Transfinite Numbers, is this YouTube video. And I will say, I think he does a much better job of explaining it than I am. So he's definitely a big inspiration for what I want to do in terms of my own content in the future. So I figured if there's any major thing to take away from this lesson besides everything about Transfinite Numbers, go definitely check out Vsauce.
There's 41. And then there's 42, and 43, a billion, a trillion. You know, no matter how big of a number you can think of, you could always go higher.
Yep. So, like I was saying, think of any natural number, you could think of a number bigger than that. That's what it means to have an infinite set, right? Or a countably infinite set.
So there is no biggest last number. Except infinity? No. Infinity is not a number. Instead, it's a kind of number. You need infinite numbers to talk about and compare amounts that are unending. But some unending amounts, some infinities, are literally bigger than others.
Yep. That's why we have all the different alepphs.
Let's visit some of them and count past them. First things first, when a number refers to how many things there are, it is called a cardinal number.
Hey, there we go. There's a term from set theory related to cardinality.
For example, 4 bananas, 12 flags, 20 dots.
It's just the amount of items you have in that set.
20 is the cardinality of this set of dots. Now, 2 sets have the same cardinality when they contain the same number of things.
That's a bijection. And he's probably going to show them matching.
We can demonstrate this equality by pairing each member of one set 1-to-1 with each member of the other. Same cardinality, pretty simple. We use the natural numbers, that is 0, 1, 2, 3, 4, 5, and so on, as cardinals whenever we talk about how many things there are. But how many natural numbers are there? It can't be some number in the naturals because there'd always be 1 plus that number after it. Instead, there's a unique name for this amount. Aleph null.
Yep. The size of the natural numbers. And he kind of already jumped to it, right? Aleph null is bigger than any individual number you will ever find in the set of natural numbers. That's kind of by definition of being able to do that. Thing is that you propose that. Okay. Oh, what do we propose here? We'll run out of numbers to name. Every single number. Yep, probably. Probably will run out of numbers. 10 to the 10 to the 10. Yep, exactly. Imagine creating a number so big that you literally couldn't write down the number in our universe, in our observable universe. Like, there's literally not enough paper that can be printed. Even if you write the number so small that each digit is a Planck length, right? The smallest that it makes in physical sense. That number is still going to be less than infinity. I mean, infinity is a thing in the sense that we're just going to head that direction. I like how he describes it as a kind of number, but I think I'll also stick to just calling it a direction, right?
Aleph is the first letter of the Hebrew alphabet, and Aleph Null is the first.
You think any other smart life forms could have scaled infinity as easy as kindergarten level math? And how would that impact our view on math? Yeah, that's a good question. The thing is, I feel like you could describe set theory to a very young audience, but you definitely wouldn't be able to use the same terms, right? Cardinality is a mouthful. You'd probably just say, oh, how big is the set, right? I think any kid can understand what it's like to count things, right? The more I think about this, though, yeah, like, adults have a hard enough time struggling with infinity. Can you think of like what would a kid imagine infinity being, right? They probably imagine it just being really, really big, right? Not necessarily like unending, just bigger than anything they can imagine. I don't know, man, maybe there'd be an easy way to say it. I'm sure you could teach set theory to like kindergartners. It probably would spook them a little bit if they were to think too hard about it.
Smallest infinity. It's how many natural numbers there are. It's also how many even numbers there are, how many odd numbers there are. It's also how many rational numbers, that is.
Yep, so again, we're kind of getting into... And he's also kind of doing it subtly here, right? He's showing that as long as you pair every number in a set with one from the natural numbers, you should be able to consider that set countably infinite. Rational numbers that go positive and negative forever and ever. Yep, exactly.
Is fractions there are. That may sound surprising, since fractions appear more numerous on the number line, but as Cantor showed, there's a way
The goat.
to arrange every single possible rational such that the naturals can be put into a one-to-one correspondence with them. They have the same cardinality.
This fucked me up the first time I saw it. So, again, look, he's literally just drawing a line from one number to another number and going back and forth. I forget what the name of this proof is called, but this is basically like a simplified version of the proof that says, oh, this is how you map every rational number to the natural numbers.
Point is, Aleph Null is a big amount. Bigger than any finite amount. A Google...
How do you get to understand this? I think you just listen to it enough times before it starts sounding intuitive. You get better understanding about the foundations of set theory. There's one of my favorite mathematicians, Matt Parker, said, there's a trick mathematicians do, which is called not worrying about it. I think you kind of have to accept some things in math in order to get past it, but there is... If you dig down enough, you will find at least some logic that explains it. It's just being able to kind of put in the work to understand it, I think. The biggest takeaway from all of that, and all of that crazy mapping that he just did, the whole point of that is that as long as you can order numbers in a specific way, as long as you can say, well, this number is going to be index 0, this one's 1, this one's 2, this one's 3, and so on, you have a countably infinite set. And that's kind of just, again, that kind of speaks to what it means to have something countably infinite. And I mean, he will go in this video as to why you can't do that with the reals, right? So
a big amount. Bigger than any finite amount. A Googleplex? A Googleplex factorial to the power of a Googleplex to a Googleplex squared times Graham's number? Aleph Null is bigger. But we can count past it. How? Well, let's use our old friend, the supertask.
Also a really good video. All the supertask really does is fit an infinite amount of steps in a finite amount of time. It's basically another word for transfinite recursion, essentially. But I like this video a lot. He Vsauce has a very Michael of Vsauce has a very good sense of humor as well. He turns like part of this into like almost a talk show a bit, where he talks about baking a cake that's infinitely big. Good video. If you are interested in like sciencey and math videos, definitely check out his other stuff.
If we draw a bunch of lines and make each next line a fraction of the size and a fraction of the distance from each last line, well, we can fit an unending number of lines into a finite space.
Yep, all it is just another way of framing how do you visibly show an infinite number of steps, right? You can imagine this line going on forever, and then when it gets to where my cursor is here, that's how you know you've gotten to the end of the natural numbers.
The number of lines here is equal to the number of natural numbers that there are. The two can be matched 1 to 1. There's always a next natural, but there's also always a next line. Both sets have the cardinality Aleph null. But what happens when I do this? Now, how many lines are there? Aleph null plus 1? No. Unending amounts aren't like finite amounts. There are still only Aleph null lines here because I can match the naturals 1 to 1 just like before. I just start here and then continue from the beginning. Clearly, the amount of lines hasn't changed.
Yep, and this is kind of what I meant by Aleph null doesn't play nice arithmetically with other numbers, right? It doesn't matter if you add 1, 2, 3, Aleph null, if you multiply it by any number, the cardinal you get on the other end of that equation is still going to be Aleph null.
I can even add 2 more lines, 3 more, 4 more. I always end up with only Aleph null things. I can even add another infinite Aleph null of lines and still not change the quantity.
Aleph null plus Aleph null equals Aleph null.
Every even number can pair with these and every odd number with these. There is still a line for every natural. Another cool way to see that these lines don't add to the total is to show that you can make this same sequence without drawing new lines at all. Just take every other line and move them all together to the end. It's the same thing.
Yep. And again, I mean, the subtext is there too, right? He already said the number of odd numbers and even numbers is equal to the number of natural numbers. This is kind of another way of visually showing that, right? You just pull out the even numbers, stack them one next to each other. You have 2 infinite sets, but they're still going to just add up to Aleph null.
But hold on a second. This and this may have the same number of things in them, but clearly there's something different about them, right? I mean, if it's not how many things they're made of, what is it? Well, let's go back to having just one line after an Aleph null sized collection. What if, instead of matching the naturals 1 to 1, we insist on numbering each line according to the order it was drawn in? So we have to start here and number left to right. Now, what number does this line get?
And here we start getting into the talk of ordinal numbers, right? Because what he's saying is we're no longer concerned with the count of the lines here. We're concerned with their physical placement on the number line, just in terms of where the order kind of leads you to, right? So this line, even though technically it doesn't add anything to the count, and I think he says that exactly, this line doesn't add anything to the count, but it still shows up after all of these other lines have kind of been drawn.
In the realm of the infinite, labeling things in order is pretty different than counting them. You see, this line doesn't contribute to the total, but in order to label it according to the order it appeared in, well, we need a set of labels, of numbers, that extends past the naturals. We need ordinal numbers. The first transfinite ordinal is omega, the lowercase Greek letter omega. This isn't a joke or a trick. It's literally just the next label you'll need after using up the infinite collection of every single counting number first. If you got omegeth place in a race, that would mean that an infinite number of people finished the race, and then you did.
That's probably my favorite description of what omega is, actually. If an infinite if you got omega place in a race, then that means that literally an infinite number of people, all the finite places, would have finished before you did. I like that description a lot.
After omega comes omega plus 1, which doesn't really look like a number, but it is, just like 2 or 12 or 800. Then comes omega plus 2, omega plus 3. Ordinal numbers label things in order. Ordinals aren't about how many things there are. Instead, they tell us how those things are arranged.
Yep.
Their order type. The order type of a set is just the first ordinal number not needed to label everything in the set in order.
That's actually a much better way of describing what I was trying to explain earlier. So I was about to say, ordinality and order type is one of the harder concepts, I think, to describe here. But yeah, the first lowest number not needed to describe something in the set. Omega plus, the fish understands. Awesome. Great, I'm happy. You have good omega plus. Yes.
So, for finite numbers, cardinality and order type are the same.
Yes.
The order type of all the naturals is omega. The order type of this sequence is omega plus 1, and now it's omega plus 2. No matter how long an arrangement becomes, as long as it's well ordered, as long as every part of it contains a beginning element, the whole thing describes a new ordinal number. Always. This will be very important later on. It should be noted at this point that if you are ever playing a game of who can name the biggest number, and you are considering saying omega plus 1, you should be careful. Your opponents might require the number you name to be a cardinal that refers to an amount. These numbers refer to the same amount of stuff, just arranged differently.
Yep. So that's the biggest distinction really with transfinite ordinals versus transfinite cardinals, right? They're not so much describing the number of elements they have, they're just describing how they're arranged. Much more succinct way of putting it, I think.
Omega plus 1 isn't bigger than omega, it just comes after omega. But Aleph Null isn't the end. Why? Well, because it can be shown that there are infinities bigger than Aleph Null, that literally contain more things. One of the best ways to do this is with Cantor's diagonal argument.
There we go.
In my episode on the
diagonalization proof.
Banach-Tarski paradox, I used it to show that the number of real numbers is larger than the number of natural numbers. But for the purposes of this video, let's focus on another thing bigger than Aleph Null, the power set of Aleph Null.
Ooh.
The power set of a set is the set of all the different subsets you can make from it. For example, from the set of 1 and 2, I can make a set of nothing, or 1, or 2, or 1 and 2.
Yep. Very quick and easy way of describing power sets. Just pick a certain number of elements from your original set, also include the empty set and the original set you started with.
The power set of 1, 2, 3 is the empty set, 1, and 2, and 3, and 1 and 2, and 1 and 3, and 2 and 3, and 1, 2, 3. As you can see, a power set contains many more members than the original set. 2 to the power of however many members the original set had, to be exact. So, what's the power set of all the naturals? Well, let's see. Imagine a list of every natural number.
And now we get into his explanation of the diagonalization proof. It's going to be slightly different than what I showed. I showed a very simplified version. So this is probably going to be... Actually, no. Now that I think about it, I think this is pretty much identical. He just uses a slightly different notation, but he's also doing like binary arguments. You'll see. Sorry, I got ahead of myself there.
Cool. Now, the subset of all, say, even numbers would look like this. Yes, no, yes, no, and so on. The subset of all odd numbers would look like this. Here's the subset of just 3, 7, and 12. And how about every number except 5? Or no number except 5? Obviously, this list of subsets is going to be, well, infinite. But imagine matching them all one-to-one with a natural. If, even then, there's a way to keep producing new subsets that are clearly not listed anywhere here, we will know that we've got a set with more members than there are natural numbers. A bigger infinity than Aleph Null. The way to do this is to start up here in the first subset and just do the opposite of what we see. 0 is a member of this one, so our new set will not contain 0.
Is this how Minecraft generates worlds? That's a good question, actually. It's some sort of procedurally generated algorithm that's probably coming up with like a probability of like what biome you're in and how the biome is arranged and what structures are nearby. It's definitely going to be doing some binary operations in order to put you in the middle of the ocean. Sure.
Next, move diagonally down to 1's membership in the second subset. 1 is a member of it, so it will not be in our new one. 2 is not in the third subset, so it will be in ours, and so on. As you can see, we are describing a subset that will be, by definition, different in at least one way from every single other subset on this Aleph Null-sized list. Even if we put this new subset back in, diagonalization can still be done. The power set of the naturals will always resist a one-to-one correspondence with the naturals. It's an infinity bigger than Aleph Null. Repeated applications of power set will produce sets that can't be put into one-to-one correspondence with the last, so it's a great way to quickly produce bigger and bigger infinities. The point is, there are more cardinals after Aleph Null. Let's try to reach them. Now remember that after omega, ordinals split, and these numbers are no longer cardinals. They don't refer to a greater amount than the last cardinal we reached, but maybe they can take us to one. Wait. What are we doing?
What are we doing? Just doing some math.
Aleph Null? Omega? Come on, we've been using these numbers like there's no problem. But if at any point down here, you can always add 1. Always. Can we really talk about it, this endless process, as a totality and then follow it with something? Of course we can. This is math, not science. The things we assume to be true in math are called axioms, and an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is.
Yes, and this is starting to get into the discussion of like what zermelo-frankel set theory is based on, right? It's axioms. It's based on things we set true. But that also doesn't necessarily mean we could set anything to be true, right? There has to be some discussion, I think, and some agreement on what we consider to be true early on. Like, I would assume it took a long time for mathematicians to be able to say that the 9 axioms... Yeah, time to make divided by 0 doable. Yep, exactly, the axiom of dividing by 0. We can do it, and it has a value. Yeah. I don't know. LeBron accidentally started. That's what happened to LeBron Stantonopoulos, the resonance cascade. Thanks, LeBron. Yeah, I don't know the history as to how mathematicians came up with the axioms they did. You know, like, I mentioned earlier, kind of offhandedly, the axiom of choice is very controversial. And there's actually a lot of frames of mathematics where they don't consider the axiom of choice to be true. And he made a reference to another video he made about the Banach-Tarski paradox. And that's actually that paradox is a direct result of assuming the axiom of choice to be true. Axiom of choice, very, very succinctly, is basically you can say you have an irrational number without being able to write it out fully. That's basically what it is. We could just say that we have a number even if we can't properly write it all out. So saying that pi has a definite value is kind of like a side effect of the axiom of choice, right? So it's one of those things, like, I think you could debate whether or not we should be allowed to do that all you want. There's value in us being able to do that, I think. I don't really know what the implications of us not having it would be. The interesting thing about the axiom of choice, though, is kind of like continuum hypothesis. There is no inconsistency if we assume it to be true or assume it to be false. Like, it works with our frame of math either way. So I'd say just consider it to be true. Why not? If it makes you do more math, sure. But the point is, we don't just add these axioms willy-nilly, right? We add them because we think that there's kind of a reason behind it, or we think that it's going to provide some sort of value. I'd be interested in studying more on zermelo-frankel to see, like, how they came about to decide the axioms they did.
Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves. If the axioms we declare to be true lead us to contradictions or paradoxes, we can go back and tweak them or just abandon them altogether, or we can just refuse to allow ourselves to do the things that cause the paradoxes.
Okay, so that's probably the answer that I was looking for then, right? Is that the debates that probably went in to figure out what those axioms are was probably just repeated instances of realizing, wait a minute, this axiom doesn't make sense because it leads us to some contradicting answers. The axioms are all, when they work together, indicative of a consistency in math. Banach-Tarski paradox is an example of an inconsistency that arises because of the axiom of choice, but we can just accept that that just happens sometimes, and we can ignore that. That's another really good video, but that's way headier than any of this stuff, so viewer discretion on that one.
That's it. What's fascinating, though, is that in making sure the axioms we accept don't lead to problems, we've made math into something that is, as the saying goes, unreasonably effective in the natural sciences. So to what extent we're inventing all of this, or discovering it, it's hard to say.
Now there's a very good philosophical question for you. Was math invented or discovered? I don't think there's a very good answer to that, but it's really fun to think about. Up and Atom has a really good video that kind of talks about it, and it actually talks about kind of this whole discovery of the foundations of math anyway, right? I call it discovery, it might as well have been development of it. But it hints at a very similar thing, right? The idea that physicists can model a universe that has different fundamental constants. We know we can model how a universe acts if the speed of light is twice as fast, or if time goes backwards, or if the decay of certain particles was different. We can't mathematicians can't model a universe where 1 + 1 doesn't equal 2. So that's something interesting to think about. Math discovered. I kind of think the language of math was developed by humans, but math itself is probably a discovery. I don't know. Hard to say. Just like Michael said.
All we have to do to get omega is say, let there be omega, and it will be good. That's what Ernest Zermelo did in 1908 when he included the axiom of infinity in his list of axioms for doing stuff in math.
Hey, there's zermelo-frankel. Zermelo of zermelo-frankel, excuse me. And there's the axiom of infinity.
The axiom of infinity is simply the declaration that one infinite set exists. The set of all natural numbers.
Yeah. He started off by creating a rule that said, hey, we have a set of infinite numbers. Concepts like algebra, geometry, trigonometry are human found. Yes, I would agree with that. At least in terms of kind of like our applications, right? The certainly sine, cosine, and tangent are is a language that we ourselves created to describe how angles and like sides work with each other. Even calculus, I'd agree with that, like the notation as well. I mean, I think the concept of like change, but that's the thing, right? It's like how much of it. I would argue that maybe there's a distinction in terms of like how much humans really discovered or developed, and how much of it was just nature doing its own thing, right? Like the concept of change is always something inherent in nature, but calculus is something that humans only could have come up with. Algebra was literally made to calculate anything economical easier. Yep, being able to model anything, being able to kind of create like linear relations, exponential relations, and geometry used to understand shapes, therefore lead to construction. Yep, exactly. So, yeah, you've said it a lot too, Zaf. Math is a tool, right? It's a tool that humans have in order to kind of describe the world around them.
If you refuse to accept it, that's fine. That makes you a finitist, one who believes only finite things exist.
Now, he's referencing other foundational theories of mathematics, right? This happens to be a foundation in which infinity is not something we just take for granted. It's not something that we can just assume exists. Which is honestly probably the more natural reaction, but I don't know. It's more fun to think about infinity.
But if you accept it, as most mathematicians do, you can go pretty far, past these, and through these. Eventually, we get to
Wouldn't what you said fall under axiom because the calculations in them worked? Yeah, so, and maybe that's kind of a good way of describing like what an axiom is actually saying. Um, you can basically decide whatever you want to be an axiom in math, right? And that's also what Vsauce Michael was kind of saying earlier on as well, right? So we are able to determine like these shapes have this number of sides, or this function. I'm trying to think of a good example. I guess certainly the fact that like I guess a triangle happens to have a right triangle has 90 degrees. How about that? Like you could say that that's like an axiom. That's a property of a right triangle. And then from there you can determine, okay, here's what sine and cosine and tangent mean, and voila, you've developed all of trigonometry. But the question is, can you prove that this is a right triangle in other ways, or do we have to just keep it as an axiom? And I think that's what the foundational, like the mathematicians who were looking for foundations of math were trying to do. They were trying to see how far back it goes. Like, what is a right triangle having 90 degrees a consequence of, essentially? So, like I said, zermelo-frankel set theory just requires that only 8 of these rules actually have to be defined from the start, and then you can basically get to all of mathematics.
Omega plus omega, except we've reached another ceiling. Going all the way out to omega plus omega would be to create another infinite set. And the axiom of infinity only guarantees that this one exists.
Yeah, so this is something I kind of glossed over in my explanation. He's about to pull out another axiom of zermelo-frankel.
Are we going to have to add a new axiom every time we describe Aleph Null more numbers? No. The axiom of replacement can help us here. This assumption states that if you take a set, like say the set of all natural numbers, and replace each element with something else, like say bananas, what you're left with is also a set. That sounds simple, but it's incredibly useful. Try this. Take every ordinal up to omega, and then, instead of bananas, put omega plus in front of each.
Yeah, I don't really like the banana example. I think that kind of leads you away too much from what the heart of the issue is. But this is exactly what I was doing when I was saying, now let's add 2 omega every natural number. What would the limit of that be? That's basically the same thing. That's pulling out the axiom of replacement, essentially.
Now we've reached omega plus omega. or omega times 2. Using replacement, we can make jumps of any size we want, so long as we only use numbers we've already
There's not enough
achieved.
bananas.
We can replace every ordinal up to omega
to make a
with
thermonuclear bomb. Yeah, how many bananas do you need to have, like, the radiation equivalent of a thermonuclear bomb? It's probably a lot of bananas. LeBron said. Now, here's a question. How many bananas would it take to create a black hole? And how much would you need to compress them, and how would that affect your ability to trick shot in battle bit? That's a good question. That's an exercise left to the reader.
Times it to reach omega times omega. Omega squared. We're cooking now. The axiom of replacement allows us to construct new ordinals without end. Eventually, we get to omega to the omega to the omega to the omega to the omega, and
that monstrosity.
We run out of standard mathematical notation. No problem. This is just called epsilon naught.
Haha, cheat code. Divide bananas by 0. Can we model dividing a shape by 0? I bet we can. I'm being ripped apart from the reality's fabric tear. You did it. You divided by 0.
And we continue from here. But now, think about all of these ordinals. All the different ways to arrange
Long John himself would divide by 0 if he could, I guarantee it.
Aleph null things. Well, these are well ordered, so they have an order type. Some ordinal that comes after all of them. In this case, that ordinal is called omega 1.
It's slightly hand-wavy here, but the whole point is that omega 1 comes far after this. Notice that he also never got into any of the, like, zeta naught, eta naught, Pfefferman shoot, or anything like that. And to be fair, it's not like he needed to. All he's doing is showing that there are bigger ordinals, but that you still will never be able to reach omega 1 doing all this.
Now, because by definition, omega 1 comes after every single order type of Aleph null things, it must describe an arrangement of literally more stuff than the last Aleph. I mean, if it didn't, it would be somewhere in here. But it's not. The cardinal number describing the amount of things used to make an arrangement with order type omega 1 is Aleph 1. It's not known where the power set of the naturals falls on this line. It can't be between these cardinals because, well...
Did you see that little text there? This is the cardinality of the real numbers. Yep. And like I said, this is provable. I didn't take the time to really prove it, but yep. We know for a fact that the size of the real numbers is 2 to the Aleph null. We don't know how that compares to Aleph 1.
Falls on this line. It can't be between these cardinals because, well, there aren't cardinals between them.
Yep.
It could be equal to Aleph 1. That belief is called the continuum hypothesis.
Yep. The idea that when you're jumping from Aleph number to Aleph number, there is nothing in between these power sets except for another Aleph number, right? So if the continuum hypothesis wasn't true, then 2 to the Aleph null is going to be greater than Aleph 1. And then we wouldn't really be able to say what the relationship is other than it's just greater, right?
But it could also be larger.
Yep.
We just don't know. The continuum hypothesis, by the way, is probably the greatest unanswered question in this entire subject.
It is.
And today, in this video, I will not be solving it, but I will be going higher and higher.
Love the diversion there.
To bigger and bigger infinities. Now, using the replacement axiom, we can take any ordinal we've already reached, like, say, omega, and jump from Aleph to Aleph all the way out to Aleph omega. Or heck, why not use a bigger ordinal, like omega squared, to construct Aleph omega squared? Aleph omega 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 omega.
Yep. Bigger and bigger and bigger ordinals. Bigger cardinals, too. You definitely can do that with cardinals as well, which I didn't really get into, but yeah, you can certainly do that. Too big.
Our notation only allows me to add countably many omegas here, but replacement doesn't care about whether or not I have a way to write the numbers it reaches. Wherever I land will be a place of even bigger numbers, allowing me to make even bigger and more numerous jumps than before. The whole thing is a wildly accelerating feedback loop of embiggening. We can keep going like this, reaching bigger and bigger infinities from below.
Yep. Can keep going forever. I mean, that's what infinity means.
Replacement and repeated power sets, which may or may not line up with the Alephs, can keep our climb going forever.
In the Beth numbers, they do.
So clearly, there's nothing beyond them. Right? Not so fast. That's what we said about getting past the finite to omega. Why not accept as an axiom that there exists some next number so big no amount of replacement or power setting on anything smaller could ever get you there?
I mean, we don't really have this axiom. He's gonna go. I'm not gonna spoil it. I'll just let him say it.
Such a number is called an inaccessible cardinal because you can't reach it from below. Now, interestingly, within the numbers we've already reached, a shadow of such a number can be found. Aleph Null. You can't reach this number from below either.
And I mean, when I was talking about like ordinal numbers and all that, right? There's several points that you can kind of say, well, we can't reach this ordinal just by doing the same activities that we've been doing, right? We have to kind of change up how we reach the ordinal. Like you can create, the Veblen functions are kind of defined such that you can extend it to be able to describe what Pfefferman shoot looks like. But there are ordinals that you cannot use, that you can't access with Veblen functions, right? Same definitely goes for cardinals. There probably is a cardinal like what he's describing out there. You probably don't really need an axiom to say that, though. I think just by virtue of the fact that by going through this process of creating bigger and bigger numbers, we have to accept that there's going to be stuff we can't reach doing this method. I mean, if we could, then we probably wouldn't have this whole notion of there being uncountably infinite sets in the first place, right?
All numbers less than it are finite, and a finite number of finite numbers can't be added, multiplied, exponentiated, replaced with finite jumps a finite number of times, or even power set a finite number of times to give you anything but another finite amount. Sure, the power set of a millinillion to a googolplex to a googolplex to a googolplex is really big, but it's still just finite.
Yep. Doesn't matter how big your input to the power set is. Unless you're putting in an infinite set, it's just going to give you a finite number.
Not even close to Aleph Null, the first, smallest infinity. For this reason, Aleph Null is often considered an inaccessible number. Some authors don't do this though, saying an inaccessible must also be uncountable, which, okay, makes sense. I mean, we've already accessed Aleph Null. But remember, the only way we could...
That was his Banach-Tarski paradox video, by the way.
...is by straight up declaring its existence axiomatically.
Oh, you're smelly, Zaf. Zaf, you smell like the power set of Aleph 1.
We will have to do the same for inaccessible cardinals.
What? No, it's a... I'm gonna guess... Yeah, it's a LeBron-Stantonopol. They grow big like this. I'm guessing it's like a Gala or something. I have no idea. I didn't think Gala apples were this dark though. That's the thing. Like, it's not a Red Delicious because Red Delicious are kind of skinny. Could be like a Gala or something. I like that you just noticed the apple. That's awesome.
It's really hard to get across just how unfathomable the size of an inaccessible cardinal is. I'll just leave it at this. The conceptual jump from nothing to the first infinity is like the jump from the first infinity to an inaccessible. Set theorists have described numbers bigger than inaccessibles. each one requiring a new large cardinal axiom asserting its existence, expanding the height of our universe of...
Okay, I am not going to be able to describe anything that shows up in this chart. All it's really saying is that mathematicians kind of have different ways of categorizing numbers as well as the processes needed to reach these numbers. Ramsey theory is a family of kind of basically word problems where you describe how many elements of certain sets there are based on certain conditions. And the cool thing with Ramsey theory is that every solution in Ramsey theory is finite. It's just really, 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 really big.
Numbers. Will there ever come a point where we devise an axiom implying the existence of so many things that it implies contradictory things?
We probably won't devise anything like this, as I think our axioms are set up to avoid that kind of thing, right? If we can write a massive textbook on why 1 plus 1 equals 2, then certainly we can use those same principles to prove that 0 doesn't equal 1.
Will we someday answer the continuum hypothesis? Maybe not, but there are promising directions. And until then, the amazing fact remains that many of these infinities, perhaps all of them, are so big, it's not exactly clear whether they even truly exist or could be shown to in the physical universe.
Yep.
If they do, if one day physics finds a use for them, that's great. But if not, that's great too. That would mean that we have, with this brain, a tiny thing a septillion times smaller than the tiny planet it lives on, discovered something true outside of the physical realm. Something that applies to the real world, but is also strong enough to go further, past what even the universe itself can contain or show us or be. And as always, thanks for watching.
Yep. And that's the end of the video. Yes, Zaf. Any questions? I guess I'll go ahead and close out this box here. Hello, Zaf. What's up? This is Poggers. Math video. Yes, yes. Yeah, thank you so much, Zaf, for joining, and thank you anyone else who might be watching and lurking in the chat here. This was a very interesting experience for me, you know. This was one of my first attempts to explain a topic of this complexity. I am definitely going to kind of review it to make sure that any future explanations I do are a little bit better. But yeah, I'm really glad I made this video. I hope you were... I understand the topics I went over are super complex, but I hope you're able to get little nuggets of information here and there. So I'll probably publish the notes I used for this video on Twitter. My username is the same there as it is here. It's radnomad. And yeah, look forward to the next math video, and feel free to give me some suggestions on future videos. Zaf, I know you want videos talking about logarithms and trigonometry, so I'd be interested in putting something together like that sometime soon. But yeah, this was quite an experience. Hope you enjoyed it. Do you want a game for a bit? Yeah, that sounds good. Let me wrap up the stream here, and then I will jump on some sort of game with you. Okay. So yeah, thanks everyone for joining. I'll see you all in the next video. I don't have any other streams scheduled for later this week. I might do a surprise stream later. We'll see. But yeah, no, this was an experience for sure. So go ahead and take a peek here.
Time.
Looks like Portia Pig is still streaming. I don't know how much longer she's going to stream, but I'm going to go ahead and raid her. I really need to come out with like a thanks for watching screen so you don't always have to see me fumbling around with starting a raid. Okay. Thank you so much everyone for joining. I'll see you in the next video.